introduce it to you. It's not a big deal though. It's electrochemistry. You need to know a little bit of it in biochem, but not everything. All right, so chapter 20, electrochemistry. We're talking about electrochemistry. It's the study of the relationships between electricity and chemical reactions, and it includes the study of both spontaneous and non-spontaneous processes. So when we're talking about electricity, right, we're talking about electrons, right? It's the fact that we have electrons that are being transferred in our chemical reactions that, is the, when we're talking about electrochemistry. So just as a quick reminder, there's a synopsis of assigning oxidation numbers. This is all the way back from chapter 4. So if you need to review on oxidation numbers, go all the way back to chapter 4, because you need to understand oxidation numbers for this chapter. If you don't, you will not be able to do the work that's necessary of you. So make sure you go through and work through this if back in chapter 4, if you don't remember this. For a quick reminder, so elements like pure elements have an oxidation number of 0, right? So if we're talking 0, sodium metal has it's a 0, right? A monoatomic ion has a charge, right? So if you have an Na plus, right, that's a +1 charge, or a magnesium 2 plus, right? Oops, I have a plus charge. Really bad too, but you get the point. Fluoride has a -1 charge, right? We're talking about fluorides, -1. Chloride, same thing, right? Oxygen is always going to be a 2- charge, unless we're talking about a peroxide, right? If we have a HOO-, right? A peroxide ion or some type of ROO-, it's the oxygen atom here has a 1- charge, both of these oxygens. So other than that, oxygen is always going to have a 2- charge, and we will, for most of these reactions, we'll be referring back to the fact that oxygen has a 2- charge. Hydrogens are always going to be listed as +1, right? It's always going to be given a +1 charge, unless it's a metal hydride, right? Unless you have, for example, sodium hydride, something like this, then this H is now going to be the minus charge, right? The sodium is plus, and the hydrogen is going to be negative. So, but in the case of most other substances, when you have an oxygen, in the case of water, right, the protons here are all going to be +1 charge. And then the sum of the oxidation numbers equals the overall charge in a and if we have a compound, a pure substance, right, the overall charge in that entire substance is going to be 0, right? So there's a difference between, right, H2SO4, this overall charge is going to be 0 for the molecules. When you add up all the charges, you end up with 0. Whereas if you end up with HSO4-, right, your overall charge here is going to be -1 because you have a negative charge left on your molecule. So as a quick reminder, I'm not going to cover it again, but these are the rules right out of the slides from chapter 4. So I copied and pasted them in here, and they kind of go through the description I just did on the previous slide. So they're here. You can work through them. You can refer back to them. Looks like the text is off size between the 1, 2, and 3, and 4. All right. Oxidation numbers. So to keep track of what loses electrons and what gains them, we assign oxidation numbers. If the oxidation number increases for an element, that element is oxidized. If the oxidation number decreases for an element, that element is reduced. And we're going to be talking about oxidation. So there's multiple ways that this is referred to in the literature. It can frequently be called oxidation, reduction reactions. Really bad handwriting today. Or it could also, you frequently will see them referred to as redox reactions. Redox and oxidation. It doesn't make a difference which comes first. Whenever you have a reaction that's occurring, right, we have one substance that's going to be oxidized, another substance is going to be reduced. And there are a couple mnemonics that I'll introduce to you. One's on this slide. You know, when you learn the oil rig mnemonic, where basically oxidation is loss and reduction is gain, right? So whenever you have an oxidation reaction occurring, right? Yeah, for example here, this sample reaction, right? The zinc the zinc metal is starting at zinc 0, right? And it's going over into the zinc chloride. So it becomes a zinc 2 plus. So, right, we have, this is an oxidation, right? Because we're just losing electrons. We went from a 0 to a +2. That means we lost 2 electrons in order to get to the +2 charge. Whereas on the other side, we have our H plus, right? HCl, this is an H plus. And in pure form here, we have H0, where hydrogen in its pure elemental form is H0. And you can see what happens, right? The chloride ion stays as a -1 in both cases. So it's just a spectator ion. So the chloride ion, nothing happens to, it's not oxidized or reduced. We'll be going through all of these in more detail. So if this doesn't make perfect sense, it's fine. That's what this entire chapter is, going through understanding that. All right. So a species is oxidized when it loses electrons. So in the last example, right, zinc loses 2 electrons, forming the zinc 2 plus ion. That's an oxidation, right? You know, because in order to go from a zinc 0, right, if you go from a zinc 0, you're going to go to a zinc 2 plus. Oops. Thinking ahead of myself. You're going to be going to a zinc 2 plus. Right. There's a loss, right, of 2 electrons here. Right. And we'll talk about where these electrons go in the next slide. And then you have over here, right, a species is reduced when it gains electrons, right? So we have, again, the H plus is going to, we have 2H plus, I should say, going to H2, right? And this is going to be gaining, in this case, 2 electrons in order to do this, right? Because we have 2H plus. So you need to gain 2 electrons for hydrogen to become hydrogen 0, right? This is pure elemental hydrogen, exists as a diatomic molecule, so it's going to be a 0. So don't get confused between when we're discussing substances being oxidized or reduced with the terms down below. The oxidizing agent, right? When we talk about an oxidizing agent, it causes something else to be oxidized. So in this case, the protons are considered oxidizing agents. So they are oxidizing the zinc, right? The zinc is being the substance that's being oxidized. The protons are the things that are doing the oxidizing. So they're considered oxidizing agents. And so you can see that they're connected to one another, right? The substance that's reduced is an oxidizing agent. The substance that's oxidized is going to be, on the other hand, the reducing agent, right? It's going to cause something else to be reduced. So in this case, the zinc is losing its electrons, and those electrons are reducing the hydrogen, right? The protons to become hydrogen. So when you're going through and understanding what's going on, recognizing that something that's oxidized is a reducing agent, something that's reduced is an oxidizing agent. It's just don't get confused with the terms. And if something you think about, right, we have, right, many of you probably heard the discussion. You think about iron. Iron rusts in the presence of acid, right? So think about that when you're trying to understand what's going on, right? Pure iron, you have protons around there. The protons, or the acid that's in solution there, is going to rust the iron to form iron oxide in this case. We'll talk about more of these reactions as we go along. Here's another mnemonic for you. Here's another one. Leo the lion says grr, right? Where you can see that losing electrons is oxidation, gaining electrons is reduction. I just give you both of the possibilities. either oil rig or Leo the lion says grr, for you to hopefully remember what's going on, right? Losing electrons is oxidation. Yes, don't forget what the grr means though. Right, Anna? Very good. All right. So we look at the example, right? This is the same example, just discussing what's going on, right? We have what I've drawn over and over again. Leo the lion, or the oil rig. Yes, either one of them work. Both are the same. What's my favorite? I think I like oil rig, but it's the one I learned first. I didn't learn Leo the lion until I started teaching out of this textbook, so I learned oil rig back in the day. So it's easier for me, but high five, yes. Yeah, Brian, you're going to have to adjust yourself. The lions no longer say roar, they say grr. At least for this class. All right, let's get back to the slide here. So we have zinc. They have started off in its 0 state. It moves and becomes a 2+, right? It's oxidized. It's losing 2 electrons, right? Whereas we have the protons, they're going to the hydrogen in its 0 state, right? And there's going to be gaining 2 electrons. So you can see what's going on here, right? If one substance is losing these electrons, the other one's gaining these electrons. Is essentially a transfer of electrons that's occurring. And we don't account for that in the chemical equation, right? Because if you had electrons on both sides of the equation, just as if this was an equal sign, you would cancel the electrons out on both sides. And that's essentially what goes on when we're doing oxidation reduction reactions. Is we have this, cancellation of electrons that are being transferred, but they're there and they're moving. So let's go through an example here. So we have the nickel-cadmium battery uses the following redox reaction to generate electricity. Right? We have cadmium as a solid, reacts with nickel oxide as a solid, plus 2 water molecules as liquid to form cadmium hydroxide as a solid and nickel hydroxide as a solid. You're looking at this going, what's going on? Which is oxidized and which is reduced? So we're going to identify the substances that are oxidized and reduced first, and then we're going to indicate which is the oxidizing agent and which is the reducing agent. So, and this is where understanding how to calculate your oxidation numbers is important, right? You're going to use first the rules that are outlined earlier to assign oxidation states. First, assign oxidation states or oxidation numbers, whichever you want to call it, to all the atomic atoms and determine which elements change oxidation state. And then second step, you're going to apply the definitions of oxidation and reduction. So then we're going to look at the oxidation reduction that's occurred. So we see here, cadmium is in its 0 state. Nickel is in its 4+ state, right? You'd figure that out because you have 2 oxygens that are in their 2-, so nickel has to be in its 4+ state. Water, the protons are in the plus state. The oxygens are in 2-, just like they always are. Cadmium hydroxide, right? So now, because our hydroxide, we have our 2- for our oxygen atoms. We have since there are 2 of them, that's a total of 4-, right? That's 4- overall. We have 2 protons, so that's a 2+ overall. So you need to balance it out. So the cadmium has to have a 2+ state. And the same thing here, right? We're at the nickel, where we have 2 hydroxide molecules, so that's going to be a 4- overall. 2 protons, 2 hydrogen atoms, that's going to be a 2+ overall. And then that requires that our nickel be in its 2+ state to balance and overall have a negative charge on the molecule. All right. You can see the oxidation state of cadmium increases from 0 to 2+, right? we see an increase in the oxidation number, and that of nickel is going to decrease, right? We go from a 4 plus to a 2 plus. And this is where one of the things when we're walking through, recognizing that when this cadmium, even though it's increasing its oxidation state, in order to increase its oxidation state, it's being oxidized. It's losing electrons, right? To go from 0 to 2 plus means you have to give up 2 electrons. So don't get confused that even though you're increasing the charge, right, you're going to plus, that means you're losing electrons, right? It's being oxidized, so therefore it's the reducing agent. The nickel, on the other hand, right, it's decreasing. The oxidation state is being decreased, right? We're going from a 4 plus to a 2 plus. So to go from 4 plus to 2 plus, you have to add 2 electrons, right? So therefore, it's, when that happens, it's going to be reduced, right? The nickel is being reduced. It's going to gain electrons, so therefore it's going to be the oxidizing agent. All right. Here's a reminder for the mnemonics, right? The oil rig mnemonic, oxidation is loss, right? The cadmium is oxidized, so it loses electrons. The nickel reduction is gain, right? Nickel is reduced, so it's going to gain electrons. Or if you go, Leo the lion says grr, right? Losing electrons, right? This loss of electrons is oxidation, or gaining electrons, right? Gaining electrons is reduction. So just recall that when you're working through these problems. All right. Let's go through one sample problem. Let's go through a sample problem here. So go through the first question there. It says, what is the reducing agent in the following reaction? So you have 2Br minus plus H2O2 plus 2H plus going to Br2 plus 2H2O as a liquid. So work through and list your answer A through D in the chat box. Brian, the exam's primarily going to cover everything since the last exam, but as you can see, we're referring back to chapter 4 in this chapter, so in essence, it's cumulative. So you can't really forget anything beforehand. Got some A's and we got some B's for answers going on here. At least for some discussion, see what's going on here. We have our substances. We have our, so people think it's either Br minus, we have two of them, right? Going to Br2, right? So we essentially have our Br in our negative state going over to Br in our 0 state. And then we have hydrogen peroxide. I'll draw it out as HOH going out, right? Reacting to form water, H2O. It's really, I guess, 2H plus this to give us our 2H2Os. All right, so we're looking at our oxygen atoms here. So our oxygen atoms are, both of these oxygen atoms are in the minus state because this is a peroxide. All right, so we have two of them here going over to our two water molecules, and they're 2 minus state. Right, so which of these is the loss of electrons? Because a reducing agent, right, the reducing agent is going to be oxidized, right, which means it's going to lose, oxidation is loss, so the reducing agent is oxidized. So which of these is losing electrons? So we have our bromine going from our minus state to our 0 state. And then we have our oxygen go from our minus state to our 2 minus state, right? So you can see, sometimes it's easier to see the reduction that's going on, right? The reduction is easier to see when you see this gain of electrons. So you go from a minus, and you're going to add 2 electrons here, right, to go to the 2 minus state. Whereas here you're going to see this loss minus an electron that's going on here, right, to go over to that side. That's minus electron. Right, so that makes sense? You read the question wrong too? Yes, see, the key is reducing agent. So the answer to this one is going to be A, right? Bromine minus is being oxidized, so it's therefore the reducing agent. And so hopefully that makes sense. Any questions on that? This is the foundation of everything going forward. If it doesn't make sense, please pop your question in there. So we'll move on. Half reactions. So we've been alluding to half reactions as I've been going through the slides here. You know, when we're talking about half reactions, both each the oxidation and the reduction are going to be written and balanced as separate reactions. So we're going to do separate reactions for each of these. We're essentially breaking down our overall chemical equation, and then we're going to write about and balance a chemical equation for each of these individual oxidations and reductions. Then we're going to use them to balance the redox reaction overall. So, you know, for example, we're going to have this example here when we react tin 2+ and iron 3+, we end up with this overall reaction, right? There are obviously spectator ions floating in solution here, but we have our tin 2+ reacts with 2 iron in the 3+ state, and we can see that tin moves up to the 4+ state and iron moves into its 2+ state. Well, we have two separate reactions that are occurring here, right? Our tin that's in our 2+ state is being oxidized, right? It's moving to the 4+ state. So it's giving off 2 electrons. Everyone see here that if we go from a 2+ to the 4+, we have a loss, or we have 2 electrons that are essentially being given off from the tin. And these 2 electrons are then consumed in the next step, right? When we have our iron in the 3+ state, right, it gains those 2 electrons to become iron in the 2+ state, right? And there, since there are 2 irons, we have to gain 2 electrons, right? So each of these irons is gaining 1 electron in order to go from the 3+ to the 2+. So you can see we've kind of separated out. We have 2 separate chemical reactions occurring, right? You can, if you wanted to, I like to draw this arrow like it's coming around and essentially moving and being transferred from one substance, from one chemical equation to another chemical equation. So you can see what's going on. We have a transfer of electrons that occurs in a redox reaction. So now we're going to walk through how to overall balance a redox equation, right? So if we were in the previous step, let's just say we weren't given this 2+, right? I mean, the 2 of each of these irons. So if we were just left with tin 2+ plus iron 3+ gives us tin 4+ plus iron 2+, right? So in order, we would need to go through and look at our oxidation and our reduction reactions first, and then we're going to go through and balance the overall chemical equation. So that's what we're going to do over the next few slides, is we're going to figure out how do we balance, redox reactions, and we're going to use what's, this half reaction method, where we're going to separate the oxidation and the reduction. So we have our overall, we'll be given some type of a chemical equation, and we'll separate them into the oxidation step and the reduction step. And we'll separate out each of those. The next thing we're going to do, and this will make more sense as we work through, is we're going to balance all of the atoms except for oxygen and hydrogen. So you have this overall chemical equation. We're going to ignore any of the oxygen and the hydrogen atoms, but we want to make sure we balance our metal atoms. We want to make sure we balance, chlorides. We want to make sure we balance, sulfates. We want to make sure everything else is balanced. Then after we're done balancing everything else, then we stop and step back, and we're going to balance our oxygen and our hydrogen atoms. And we're going to do that by adding either water or protons to our equation. Again, this will make a little bit more sense as we walk through, but we'll refer back to this, this step by step as we go through the sample problem on the next slides. And then that next step is we're going to add electrons, right? Because we need to balance the overall charges that are in that reaction, right? Because the oxidation and reduction, because there's losses and gains of electrons that are occurring, the overall half reactions aren't going to be balanced, right? They're going to be missing electrons in each of those steps. So we need to balance up the overall charge in the reaction so that we have the same charge on both the left and the right-hand sides of the equation. Then we're going to multiply by a common factor to make the electrons and the half reactions equal, right? So we'll have 2 separate equations. We'll have an oxidation equation, we'll have a reduction equation, and we need to make sure that our electrons that we put in each of those equations here are equal. So that way we can, account for the fact, just like I did on this previous slide, we had 2 electrons here, right? 2 electrons here that are balanced with the 2 electrons here. So that's what we're going to be doing. We need to make sure that we balance the number of electrons in both of the oxidation and reduction equations. And then the last and final step is we're going to add the half reactions. I guess not exactly final. We're going to add the half reactions. I guess it is the final. And we do all of our eliminations. So if we have, electrons in both sides of the equation, they're going to be canceled out. We have any extra water molecules, etc., they're all going to be canceled out. All right. So this is kind of a quick synopsis, another way of looking at it. You can simplify by dividing by a common factor, right? So I'm sorry, this is at the end of the reaction equation. I'm sorry, there's couple more steps, right? If we have if our reaction is not simplified down to the lowest common denominator, so to speak, we can divide by a common factor. And then if we need to, occasionally, if we run our reaction into a basic solution, then we need to convert. We need to convert from acidic solution to basic solution. And this will make more sense as we work through a sample problem. If we're told that we're running our reaction under basic conditions, or let's just say if the reaction says you're running the reaction at a pH greater than 7, then you would need to know that you need to convert any of the protons, because remember back here we added protons. We need to remember that we need to convert those protons that are in solution or acidic solution to a basic solution. And then the last step is to double check the atoms and balance, make sure the atoms and the charges balance overall. So they make sure that you didn't add any extra protons, any extra, oxygen atoms. Make sure your charges are all the same on both sides of the equation. All right. So this is kind of an A, B, C, D of what I basically just stated over the past few bullet points. So you can come back and refer to that if it helps you out. So here's a sample problem we're going to go through. We have the reaction of manganese oxide, MnO4-, and this C2O4-. This is an oxalate O2, 2-. So we have this reaction, and they're showing you in the picture up above, right, where we are going to add this purple manganese tetroxide anion into this oxalate 2- anion solution, and the reaction occurs, up to the point where the solution remains purple, because eventually we've reacted and consumed all of our C2O4. But what's the reaction that's going on here? So the reaction that's occurring is along the way as we're adding, adding the manganese, this manganese is reacting immediately. In solution, it remains clear up until we've consumed all of the C2O4 2-. And the reaction that's occurring is a reaction with the manganese O4- is being converted to a manganese 2+. The C2O4 2- is being converted to carbon dioxide. Right, so we have an aqueous solution of carbon dioxide at the end. So first thing we need to do is assign oxidation numbers. So our manganese is sitting here. You can see that the manganese is in its 7+ state. Everybody's looking at this going, how did you get 7+? Remember, we have our oxygen atoms. Each of our oxygen atoms is a 2-. We have 4 of them, so there's an overall 8- charge here. One of those minuses is still left on the molecule, so that means we need to have the manganese as a 7+, or +7, right, charge, in order for it to balance the overall negative charges here, right? The same thing. So that becomes obviously 2+ is pretty straightforward. And the carbon atom, same thing. We have 4 oxygen atoms, so that's an overall 0. It's an overall 8-, 8- charge. 2 of those minuses are still there, so that means we have an overall 6-. So these 2 carbon atoms have to have an overall 6+ charge to balance it out, so that therefore they are converted. Each of them has to be a 3+ charge, right? On the other side, right, we have 2 oxygen atoms, so that's an overall 4- charge. We only have 1 carbon, so it has to have a 4+ charge. So if you don't remember how to do this, what I just walked through there, I'm not going to cover it in detail. You can either set up a time to meet with me separately or go back, read chapter 4. So you can see the carbon, the manganese is being reduced because it's, gaining electrons, right? Reduction is gain, right? From a 7+ to a 2+ is a gain of electrons. And the carbon going from a 3+ to a 4 plus is being oxidized. So that's the first thing, assign oxidation numbers. And I'm not going to go through these in that much detail like I just did. Just wanted a quick reminder for you, because I know it's been a while. All right, the oxidation half reaction we'll draw up first, right? We have our C2O4 is going to 2 minus is going to our CO2. Well, the first step tells us that what do we need to do? The first step we need to first step we did here, right? We need to separate out and create two half reactions. Here's one of the half reactions. I'll show you the other one in the next step. So here's the first half reaction. Then we're going to balance the atoms other than oxygen and hydrogen. So since we have 2 carbons here, we need to put a coefficient of 2 here and balance the carbon atoms. So now there are 2 carbon atoms on both sides of this half reaction. The next step is to balance the oxygen atoms. So you can see we have 4 here. We have 4, already have 4 there, right? 2 times 2, we have our 4 here. So it's already balanced. So once we've done that, the next step following this is to balance the charge. We have a 2 minus charge here. So we have 2 negative charges on the left. We need to add 2 electrons to the right-hand equation to balance the overall charge. So now there's a 2 negative on both sides. Let's do the other half reaction. So here's the other half reaction. We have our manganese O4 minus going to a manganese 2 plus. So you can see obviously the manganese is already balanced, right? We have 1 on both sides. The next step is to balance the oxygen and hydrogen atoms. There were no hydrogen, so all we need to do is balance our oxygen atoms. And the way we do that is we need to add 4 water molecules to the right-hand side of the equation, right? So now we have 4 oxygens on the left, we have 4 oxygens on the right, right? So you say, well, okay, now what? We have extra hydrogen atoms. Well, now the next step is to make sure that we balance the hydrogen atoms. So since we have 4 times 2 hydrogen atoms, 8 hydrogen atoms, we're going to add 8 protons to the left-hand side of the equation, right? So now we have our 1 manganese on either side, 4 oxygens on either side, and 8 hydrogen atoms on either side, right? So what's the next step after this, you ask, right? It's the balanced charge, right? So we look at our charges. We have 8 plus charge from the protons, a minus 1 charge from the oxygen atom. We have a 2 plus charge here, and that's it, right? So you can see overall on the left-hand side, when we add both of these together, right, this is an overall plus 7 charge. So to go from plus 7 to a plus 2 charge, we need to add 5 electrons, right? So if we add 5 electrons here, right, so 5 negative charges, then that brings this overall side to a 2 plus, right? So we have a 2 plus on the left, a 2 plus on the right, and we're balanced. Making sense so far? So this is going to be the confusing step because you need to recognize what's going on, right? We need to make sure that our charge is balanced. We don't need to make sure they're 0. We just need to make sure they're balanced. So we have a 2 plus on the right. We have to have a 2 plus on the left. Yes, I can explain to you. The manganese one is going to be, all right. And I'll even, let me just erase it all so it won't be so messy. All right. We have our 8 positive charge on from the protons. We have a 1 negative charge from the oxygen manganese oxide. We have a 2 plus charge from the manganese here. we add these two together. We end up with an overall 7 plus on the left. We have a 2 plus on the right. We need to make both of these exactly the same charge. In order to do this, we need to add 5 negative charges, right, to the left-hand side. So when we do that, right, when we add these two together, oops, that's a negative. We add these two together here, right? This ends up equaling 2 plus, right? And this is these are going to be electrons. Why does it keep doing that? These are going to be electrons. So we add 5 electrons to the left-hand side to total. So because when we have a 7 plus 5 minuses gives us an overall 2 plus. So now the left and the right-hand side of the equations both equal 2 plus. So we needed to add 5 electrons to the left-hand side of the equation to balance the overall charges in the equation. And if you look at it, right, so we have 5 minuses, 8 positives, 1 minus, and we need that equal to 2 plus, right? Which makes sense, right? 5 negatives plus 8 positives plus a 1 negative is going to be overall. We add this up as 2 plus. That makes sense? Anybody else have any other questions? All right. So now we have to combine these two half reactions together. So we put them one over the other. It's pretty straightforward. Make sure the arrows are lined up. And we need to, in order to do this, we need to balance the number of electrons in both equations. So you can see in this top equation we have 2 electrons. In the bottom equation we have 5 electrons. So we're going to use the common factor, right? We want to basically, we're going to multiply the first equation, right? Multiply this by 5 so that we can get an overall 10 electrons. And we're going to multiply the entire equation on the bottom by 2, right? Because the 2 times the 5 is going to give us our overall 10 electrons. So this is kind of our using the least common multiple to make these equal to one another. And that happens on the next slide, right? So you can easily see that, right? This is going to be 5. This is going to be 10 afterwards, and this is going to be 10 afterwards, right? This will be 10. This will be 16. This will be 2, 2, 8. Right? That's all I did, was you just basically distribute the chart, the multiply throughout the entire equation. And that's what happens here on the next slide. So we have our 2 equations. Now, since our electrons are balanced on both sides in both equations, we're going to add the 2 equations together, right? So we have our 10 electrons plus our 16 protons plus our 2 manganese oxide anions plus our 5C2O4 2 minuses is going to move over to the other side of the equation and give us our 2 manganese, our 8 water plus our 10 carbon dioxide, and our 10 electrons. So you can see we now have an overall balanced equation here. So what do we do next? Right. After that, we need to cancel out anything that appears on both sides of the equation. And in this case, 10 electrons appears on both sides of the equation. So we're going to essentially subtract 10 electrons from both sides, and the equation is now balanced. Right? So we have an overall balanced equation. We confirm that we do by simply going through, right? There are 16 hydrogen atoms on here, 16 hydrogen atoms here. We have 2 manganese atoms here. We have 2 manganese atoms here. There are 8 oxygen atoms plus another 20 oxygen atoms. Right? So 28 here. We have 8 here. plus another 20 there, so 28 oxygen atoms on the both sides. We have our 10 carbon atoms and our 10 carbon atoms. So everything's been balanced so far from that perspective. We have, overall 4 plus charge on the right-hand side of the equation. We have 16 plus or 2 negatives, right? That's 2 of these, plus 10 negatives here, right? So this side of the equation here, once you add everything up, is equal to a 4 plus. So our charges on both sides are also equal, right? So we verified that the equation is completely balanced by looking at this. And what you might notice is, obviously this equation still has charged ions on both sides, right? There are spectator ions. Maybe there's 4 chlorides, 4 Cl minuses. It could be any anion, but we could imagine that there are 4 chlorides that are on both sides of the equation, right? And they're just counterions that are floating in solution, and we're not counting them in the equation, right? So these aren't there. So we end up with charges on both sides of the equation. Our spectator ion is being ignored in this equation. Let's go through another sample. And this would look like a sample problem, right? So it's complete and balanced this equation by the method of half reactions. So we have our Cr2 O7 2 minus plus chloride going to Cr3 plus Cl2 as a gas. So you can see, obviously, this equation needs a lot of balancing, right? There are oxygen atoms on the left-hand side of the equation. There aren't present on the right-hand side of the equation, right? There's 1 chlorine here, but there are 2 chlorines there. There are 2 chromiums here, but only 1 chromium there. So you can see there's a lot of balancing that needs to go on. And we're being told that it's an acidic solution, right? So we know that means that we have protons present in our reaction mixture, right? So first thing we do is we divide the equation into 2 separate half reactions, right? So we have our chromium Cr2O7 2 minus going to Cr3 plus, and our Cl minus going to Cl2. Right? Next step, I'm going to balance each half reaction. In the first half reaction, the presence of 1 Cr2O7 among the reactants requires 2 Cr3 plus among the products, right? So the first thing we're going to do is we need to multiply the right-hand side by 2. We need 2 chromium 3 pluses on the right-hand side. Then the 7 oxygen atoms, right, and the Cr2O7 2 minus are balanced by adding 7 water atoms to the products. So we add 7 water atoms to the products. Then the 14 hydrogen atoms, right, in the 7H2O, right, there's 14 here, are added in as protons on the left-hand side. So we add 14 protons on the left-hand side. So that's the first part. We balanced all of the atoms on both sides of the equation. Next thing we need to do is we need to balance charges, right? So we have a 6 plus here. We have 14 plus. We have 14 plus here, plus our 2 minus here. So you can see that this totals 12 plus. So in order for these two sides to be equal, we need to add 6 negative charges. So we're going to add 6 electrons to the left-hand side of the equation. And now our equation is balanced. Number of atoms are balanced. The overall charges are balanced. And we can see that our chromium, right? We can see what happens to determine if this is oxidation or reduction. Our chromium here, You can go through and calculate the charges. We didn't do that here. You can go through and look and do the calculations. We have our oxygen atoms are the two minus, so we have an overall 14 negatives coming from the oxygen. 2 of them are have an overall 12 negative for the chromium. So each of these chromiums are going to have to total 12 plus. Each of these chromium is a 6 plus charge. And then on the right hand side, we're going to each of these becoming a 3 plus. So we obviously have it going from a 6 plus to 3 plus is a what? Go through from the 6 plus to 3 plus, we're gaining 6 electrons, right? That's a reduction, right? 6 plus to 3 plus is a reduction. Reduction is gain, and which makes sense. We're adding electrons to the left-hand side. Right. Second half reaction is here, right? Where we have 2 chlorine atoms. We need to balance them first, I guess, right? We needed to put 2 before the chlorine in order to balance the number of chlorine atoms, right? The second thing we need to do is balance charges, right? We have 2 negative charges going to nothing on the right, so we have to add 2 electrons, 2 negative charges, which ends up being here, right? So we have to add 2 electrons in order to balance the charges on both sides. We can see obviously our chlorine goes from a 1 minus charge here to a 0 charge on the right hand side, which makes sense. So that this is obviously going to be our oxidation, right? Oxidation is loss. So we have 2 electrons that are being given off or lost in this reaction, right? So hopefully that makes sense. Next thing we need to do is we equalize the number of electrons transferred in the 2 half reactions. To do so, we need to multiply half of the chlorine reaction by 3 so that the number of electrons gained is 2. So we're taking this entire reaction, right? I'm going to multiply that by 3 because we need these electrons, these 2 electrons, we need to be equal. Let me go back to the previous slide, to the total of 6 electrons that are here, right? So we need the 2 to be equal to the 6. So we just simply multiply the entire equation by 3. And when we do that, we end up with 6 chlorine atoms, chlorine anions, chloride anions, going to 3 chlorine as existing as a diatomic molecule. The chromium half reaction already has the 6 electrons, so we're not going to do anything to that equation. So now the equations have the balanced number of electrons, and we're going to add the 2 of them together. And I wish they would have given I should have added that in here. So 6E plus 4. It's probably easier if I just add the, right, maybe let me just do one thing. CO minus. So what we're doing is we're adding 6 Cl minus going over to 3 Cl2 plus 6 electrons, right? We're just going to add these 2 equations, and you can see that's what's going on. If you just simply add these 2 equations, and I'm not going through each step, right? We end up with this overall balanced equation here. And you can see we ended up canceling, right? There were 6 electrons on the left. There were 6 electrons on the right, and they just cancel out. Right? So we've canceled out the electrons on both sides, and we end up with our overall balanced equation. You can go through and confirm that they're correct number of atoms on both sides, right? There are 14 hydrogen atoms on the left. There are 14 hydrogen atoms on the right. There's 2 chromium atoms on the left. There are 2 chromium atoms on the right. There are 7 oxygens on the left, 7 oxygens on the right, 6 chlorines on the left, 6 chlorines on the right. Charges are balanced. We have a 6 plus charge here. we add up the charges, 14 plus, minus 2 minus, that's 12 plus, minus 6 leaves us with an overall 6 plus charge on both sides of the equation. All right. Now it's your turn. We have a few minutes to do a sample problem. Right. So it says if you complete, let me just slide this up a little bit. The other stuff's off the screen. It says if you complete and balance the following equation in acidic solution, right? This is showing us that it's acidic solution. Where you have manganese 2 plus is reacting with NiBiO3 to give us Bi3 plus and manganese O4 minus and our sodium ion. This is how many water molecules are there in the balanced equation for the reaction balanced with the smallest whole number coefficients. So you need to go through and balance the equation to get the number of water molecules that there are. So take a few minutes and try to start working through balancing this equation. And remember, when you're walking through, right, what do we do first, right? Step 1, you make 2 half reactions. Right? Step 2, you balance atoms other than O and H. Step 3, right? You balance O and H using H2O and H plus. All right, 4, you add your electrons to balance charges. Charges. And 5, multiply by the common factor. All right, you want to balance electrons, and then you add half reactions. All right, so hopefully I gave you a head start. We got about just under 4 minutes left, so do the best you can. And A through E, you have come up with an answer. Anybody struggling with the charge on the bismuth? Everyone have it properly? So if you have H2O on both sides, you have to cancel some of the H2O on both sides. So, and yes, bismuth is a 5+ overall charge, correct. So bismuth is a 5+, and if you end up with water on both sides, you have to cancel in your balanced equation, right? So you end up with might need to start in the next class with this problem. I'm going to end before I give you the answer because it's 9:20. We'll start the next class right with this. So I'll leave you in suspense. Take a few minutes. If you have time right now at the end of the class, finish working on the problem. And if not, then take some time before beginning of the next class and we'll start with this problem during the next class. And use the hints, right? You need to cancel out anything that's on both sides. Katie's in the house, so she says so. Thanks, everybody. Have a good week, last week of classes before your finals week.